All right, how's everybody doing? Man, we're missing a bunch of people. It is, but you're here, so hello. It's week 9, Friday. You guys have 1 week left in school, possibly forever. No, some of you will be back. Some of you will go on for more school, and. If you go into a PhD program, just be prepared. It could take a long time. So, but yeah, it's great. It's spring, so today and then 1 more week. So today we'll kind of cover the last bit of, I guess, stuff in chapter 9. Next week we'll spend primarily in review, just to and cover all of the finer points of hypothesis testing, confidence intervals, and statistical inference, and then you'll have your final. So okay, so we left off yesterday with hypothesis testing for sample for the mean based on a sample. So maybe we will start with a let's just get into the new stuff. I was gonna do a problem, but we'll just go for the new stuff. Okay, so we'll do confidence intervals for mu1 minus mu2 based on 2 samples here. Okay. And so the key here is that we are making a confidence interval for the quantity mu1 minus mu2, okay? And so here we want to kind of say, is there, what is the confidence interval for the difference, okay? So for example, we can ask, what is the difference between the average price of regular gas, so that would be 87, and premium, which is 91, right? So what's the difference between the average of, cost per gallon of regular gas and premium gas, okay? And so here, the the end result, the ending confidence interval, I'm hoping you guys are somewhat familiar with gas prices or something. If you ever go driving and have to fill up your tank, maybe a lot of you don't have cars, but the ending confidence interval is not going to actually have the price of any individual gallon of gas, but the ending confidence interval will be something like 16 cents to 25 cents or something like that, okay? That we're saying on average premium gas costs between 16 to 25 cents more per gallon than regular gas. So, if this is a 95% confidence interval, let's say this is our 95% confidence interval. The resulting statement would be something like, I am 95% confident that the average price, per gallon of premium gas is between, 16 cents and 25 cents more than the average price of regular gas. Okay, something like that. Okay, and that would be our confidence interval. So, maybe the current cost per gallon of regular gas, maybe perhaps if we went out and we got data, maybe the current average price of, let's say 10 randomly selected stations. We'll say in LA, just because gas prices highly depend on your location. So we'll say, maybe the current average price of 10 randomly selected stations in LA for regular, maybe the cost is something like $2.90 or something like that. I don't know. Okay, and then and here's the thing: is that a lot of times we think of going from one station at a station. We're going to go. We can look at different prices. There's an assumption here, and is that our samples are independent. Okay, and then so we would pick like another 10 random stations. And then we would look at kind of the average price for premium is something like $3.21 or something like that, or maybe that's too much, $3.11 or something. Okay. And then, you'd create the confidence interval and you'd get something like this. Okay, so we are creating a confidence interval for the quantity mu1 minus mu2. We are not creating two separate confidence intervals for the average price of regular and a separate confidence interval for the average price of premium gas. We are creating one confidence interval for the quantity mu1 minus mu2. Okay. So with that in mind, we'll create the formula for the confidence interval. Okay, so for mu1 minus mu2. Okay, so again, in the center, in the middle of our interval, what would we put? We would put our best guess for mu1 minus mu2, and what would our best guess be based on our data? Our best guess for the quantity mu1 minus mu2 would be x bar 1 minus x bar 2. Seems reasonable, right? Okay, and then we would go plus or minus the margin of error, which is always going to be our critical value times the standard error. Okay, and so as far as our critical value and standard error go for this, our critical value, because we're dealing with means, will come from the t distribution, a t star, and then our standard error, when you are dealing with the difference between two population means, the standard error is just this ugly formula, S1 squared over N1 plus S2 squared over N2. Okay. really what we're doing is we're adding the variances together and then taking the square root of the combined variances. Okay, so this is our standard error. The selection of T star depends on your confidence level and degrees of freedom. Okay, so T star depends on the confidence level and the degrees of freedom. And so degrees of freedom is equal to n minus 1. However, we have two n's, okay? We have n1 and n2. And so we will use the smaller of n1 and n2. That's the truth is that the true degrees of freedom is actually a bit more complicated, but this is kind of like the safe way to kind of approximate it. Okay, so the truth is that the actual degrees of freedom, when you're combining things like this, the true number of degrees of freedom is a bit more complicated. But just for simplicity in our class, we're going to kind of play it safe and use this n minus 1. Okay, and this will always underestimate the degrees of freedom, which in general is how you kind of play it safe. All right, so with this in mind, let's just try out a simple example here. Okay, and I've got to pull up my T star, T table. Okay, so maybe we have a question. You know, what is the average, or what is the difference between the mean weight mean weight of an orange and the mean weight of an apple? Okay, I actually have no idea. What's the average size of an apple and what's the average size of an orange? And it all depends, right? Like, what do we have? Average weight of orange. It's gonna tell me nothing. 131 grams, medium-sized orange, while larger ones weigh 184 and a smaller one, okay, this is complicated stuff. Okay, an apple, average apple between 70 and 100 grams. Okay, so we will just go off of this and we'll just make stuff up. Okay, so we'll say somehow you get, maybe you're at like the supplier for Ralph's or something. Okay, so maybe we'll say you get a random sample. And we'll say 15 oranges. Okay, and we'll say the average weight of the sample is, we'll say 130 grams, and has a standard deviation of, so it said could go between 130, so we'll say 20 grams, okay? And then somehow you get a random sample 10 apples. And we'll say the average weight of the sample is 105 grams with a standard deviation of 15 grams. Okay, and we'll say make a 95% confidence interval, and we'll ask what is the lower bound. Okay, so I'm gonna have to make up some answer choices here. And we'll try this out. Okay. I hope I did this correctly. Okay. Okay, I'm gonna cut the time and I don't know, just a little bit here. So get your clicks in, please. Okay, I'm gonna hit stop. Okay, so let's go through and identify what each of these numbers represent. Okay, so we have a random sample of 15 oranges. So we just have to arbitrarily label one of these to be sample 1 and sample 2. So in my mind, it makes sense to say the first sample we see will be sample 1, and the other one will be sample 2. But if for whatever reason you decided to call the oranges sample 2 and the apples sample 1, that's fine. Just be consistent in your labeling. So oranges, there's 15 of them, so that's going to be N1. The average weight, 130, is going to be our X bar for sample 1, X bar 1. And the standard deviation of 20 is going to be our S, standard deviation of sample 1, S1. You get a random sample of 10 apples. This is going to be N2. We have 105. That will be X bar 2. And 15 will be S2. Okay? So if I may, I'm going to just go to the next slide here. Okay? So what I have is sample 1. So I've got N1, X bar 1, and S1. And sample 2, N2, X bar 2, and S2, and I've already forgotten all of my numbers here. I had 15, and I had 10, and I had 130 and 105. And what were my standard deviation numbers? 20 and 15. Okay. Okay, and then so now it's just a matter of plugging the numbers in, X bar 1 minus X bar 2 plus or minus T star times S1 squared over N1 plus S2 squared over N2. Okay, let's figure out our T star. Our T star, we will have, how many degrees of freedom will we have? It's going to be N minus 1, and we're going to use the smaller n, so we're going to use 10 minus 1. We have 9 degrees of freedom. Okay, and at 95% confidence, the T star we're going to use at 9 degrees of freedom and 95% confidence is 2.262. Okay, so let's put all of these numbers in here. So I got 130 minus 105 plus or minus 2.262 times the square root of 20 squared over 15 plus 15 squared over 10. And if I did my math correctly, I got something like 2.262 times, this almost came out to be 7 exactly, is that right? Something like very close to 7. And then so I got 25 plus or minus or like 7 point something, maybe 7.1, I don't know. I got like 15, what did I get? 15.9 is what I got. Okay, and then so my lower bound was 25 minus 15.9, which gave me a lower bound of 9.1. and an upper bound of 25 plus 15.9, which would be something else, 25 plus 15.9, 40.9. Okay, and so our correct answer there would have been answer choice C, okay? And we would make a statement like this: I am 95% confident that the average weight of oranges, okay, and of course this is always in the population. The average weight of oranges in the population is between 9.1 grams and 40.9 grams heavier or more than the average weight of apples. In the population. Okay. So if I asked this question, does our interval provide evidence that the average weight of oranges is different from the average weight of apples. I guess we could make this a yes or no question. What do you guys say? Does our interval provide evidence that the average weight of oranges is different from the average weight of apples? You can discuss, but make a decision quickly. I'll stop the time at 1 minute. Okay, so go ahead and click your buttons here, and let's see how you guys responded. And the answer is yes. Okay, so when we look at our interval, what we see is that our interval is entirely positive, right? So our interval provides evidence that the average weight of oranges overall is heavier than the average weight of apples, okay? So basically our reasoning for yes is 0 is not within the interval. And our interval is entirely positive. Okay, so we have something like that. Yes, question.
Why do you use 10 degrees of freedom instead of something like 24?
Yeah, you know, so that's a good. So the true number of degrees of freedom is probably something around 22, 23. But yeah, there is there are a few ways to approximate the degrees of freedom. One way is to do n1 plus n2 minus 2, and we would have 23 degrees of freedom. And the truth is that the actual number of degrees of freedom will always be between this number 9 that we've come up with, n minus 1, and the other extreme, n1 plus n2 minus 2 of 23 degrees of freedom. And depending what textbook you read, the textbooks might say use n1 plus n2 minus 2. Other textbooks will say use n minus 1. The actual way to determine the degrees of freedom is by a decidedly complicated formula, and that's why we don't really teach it in the class, because you're trying to combine standard deviations from two different populations, which is it's a tricky matter. So we just say use n minus 1, and that's kind of like the safe side, and then n1 plus n2 minus 2 is like the I don't know, a little bit more I guess being liberal with the degrees of freedom. So who knows? Okay. All right, so we have this. Let me just talk about, you know, if the interval does contain 0, okay, if the interval contains 0, meaning one end is negative and the other is positive, then that means 0 is a plausible value for the difference mu1 minus mu2. Okay? So if the interval contains 0, then 0 is a plausible value for the difference. In that regard, we would say then the interval would not provide evidence that there is a difference between mu1 and mu2. So, let's say you took small samples. You have, for example, 2 small samples. You asked, maybe 10 lawyers their annual income and 10 doctors their annual income, and you want to know, is there a difference in the average annual income of lawyers and doctors, right? Or maybe I should say physicians. And so, if you have a small sample, so let's say the resulting interval was something like negative 35,000 to 65, 60,000 or something like that. Okay? And we'll say lawyers will be sample 1 and doctors will be sample 2. Then, the statement would be, I am 95% confident, or whatever, if we chose, assuming this is a 95% confidence interval, I'm 95% confident that the average annual salary of lawyers is between 35,000 less and 60,000 more than the average annual salary of doctors. Okay, and so here our data and our resulting confidence interval do not provide evidence that there is a difference between the annual average salaries. Okay. Now, if we gathered more data, we might see a difference. Okay, but at this point, we don't. Although I have to say, if you had a small sample, you probably should not make a confidence interval, because I think if you were to check your conditions, we would find that large sample condition would be violated, because I think with the salaries of lawyers and doctors, I don't think it's not safe to assume that the population follows a normal distribution, and so you would need larger samples of, like, say 25 or more. And I would say with probably, with lawyers and doctors, some people make, over $1 million a year if they're high profile lawyers or, prestigious doctors. That's certainly possible. And so you're probably going to have a very skewed distribution that these methods would not work. I'm just thinking of that as I'm, like, talking through this example here. But is this okay? Yes, question.
Does that mean the interval, does the interval here provide evidence that there is no difference?
We cannot say that, okay? So the interval does not provide evidence that there is a difference, but do not say that the interval provides evidence that there is no difference, okay? Because our intervals never provide evidence that something is a particular value. And so in that case, we still cannot say that the interval provides evidence that the difference is 0, okay? Because we don't know that. All we can say is that the 0 is a plausible value, so we can't eliminate it. But we can't say it's for sure 0 or any other value in between the interval, okay? It's the same principles for all of the other confidence intervals. Steph says basically you get a range of plausible values, and so we say we can't eliminate these possibilities. We can kind of throw away the other ones, but the stuff in here are plausible, but we don't know for sure if it's any of these actually, okay? And actually, you know, the other ones are still possible, just implausible, okay? They're not. We would be surprised if it was outside of the interval, but that is also still possible. Okay, so that is the confidence interval stuff. We also have hypothesis testing for mu1 and mu2 based on 2 samples. And I realize I only have 10 minutes here, but it's just like all of the other hypothesis testing that I feel like I can just give you the steps and you'll be fine. but we'll just make sure, okay? So same steps as before. So step 1 is create your hypotheses. Okay? So if you recall hypothesis testing for 2 samples with proportions, pretty much it's very, very similar to that. So what would our null hypothesis be? Instead of the proportions being equal, we would say what? Mu1 is equal to mu2. We're basically saying that the 2 populations have the same mean, and then the alternative would be what? Mu1 is not equal to mu2, or mu1 is greater than mu2. Well, I'm glad that was funny there. Mu1 and mu2. Okay, so we have that. Step 2 is, we do our preparation, which is really just check the conditions. And select alpha, right? Okay. Step 3 is our calculations. Okay, so 3a would be find the standard error. The standard error is S1 squared over N1 plus S2 squared over N2. Okay? Our test statistic T what do you think? It's going to be the observed versus the reality. The observed is the difference between our sample means, okay? And then technically we would have a -0 because under the null hypothesis, the expectation observed versus the expectation, the expected would be a difference of 0, but subtracting off 0 doesn't do anything, so I'm going to just ignore it, and so we have x bar 1 minus x bar 2 divided by the standard error. So that's our test statistic T. Okay. And then we would look up T in the T table. Okay. And we will say use degrees of freedom equal to n minus 1 using the smaller of n1 and n2. And again, other textbooks may have a different way to approximate the degrees of freedom, but this is what our textbook says, so we're just going to do this in our class. Okay? And then so this gives you, get your p-value, look up t in the t-table, and so we covered this, I feel like pretty thoroughly on Wednesday, how to look up your t to get your p-value, and then lastly, make your conclusion. And then so if the p-value is greater than alpha, do not reject the null hypothesis. And if the p-value is less than alpha, reject the null hypothesis. So far, so good? Okay, let's, we'll just do one more question, and this will just be kind of like, make sure we can do our t's and the p-value stuff. Okay, so I'll do one more clicker question, and this will just be on looking up a value in the t-table. Okay, so let's say, okay, so let's say alpha is equal to 0.05, okay? You have n1 equal to 15, n2 is equal to 12, and the alternative is mu1 does not equal mu2, okay? So, you have x bar 1, x bar 2, and s1 and s2, but we'll say, fast forward, your resulting test statistic ends up being, we'll say negative 2.51, okay? So what decision do you make regarding the null hypothesis? And your choices are reject or do not reject, or we'll say can't tell. I hope I gave you a good number. Oh, sorry, I gotta fire this up. Okay. So your alternative is mu1 not equal to mu2. Your test statistic ends up being t equal to negative 2.51 after you do all of the other stuff. Yeah, question. Yeah, I'll have a full sheet of equations. So on the quiz, I had like the equations relevant to proportions. So for the final exam, I'll give you an equation sheet with the proportion formulas and the means, sample means formulas stuff. Yeah, I'll post the actual equation sheet, okay? And so, yeah, over the weekend I will post a practice final exam and an equation sheet. I think it'll be helpful. All right, let's see how we're doing. So get your clicks in. Get your clicks in, please. Okay, I'm gonna hit stop here and we'll go over the answer. Okay, so we are going to use degrees of freedom equal to what? So we're going to say degrees of freedom is 12 minus 1. We have 11 degrees of freedom. And with 11 degrees of freedom, we're going to just ignore the negative sign and look up 2.51. So 2.51 is in between the column for 2.201 and 2.718. Okay, so that means our tail area is between 0.01 and 0.025. So the resulting tail is between 0.025 and 0.010. Is that so far okay? So far so good? Okay, we look at the alternative hypothesis. The alternative has a not equal sign, so we double the tail. And so our p-value is between 0.05 and 0.02, okay? Or we could just say 0.05 is greater than our p-value, which is greater than 0.02, okay? So this is what we have. We are using alpha equal to 0.05. So alpha is equal to 0.05. And so our p-value, even though we don't know exactly what it is, we do know it is between, it's less than 0.05 and more than 0.02. So we do know that the p-value is less than alpha. And that means we would reject the null hypothesis. Okay? All right. So don't be thrown off that one of your boundaries is 0.05. If you said you can't tell or something, don't be thrown off because it's not less than or equal to. It is strictly less than. The p-value is between 0.05 and 0.02, and it's not equal to 0.05. Okay, we'll end there. We'll see you guys on Monday. Have a good weekend.